All right, so the last functional group that we're going to talk about are the amides and the nitriles. Again, we're going to kind of keep them in the same place in our mind. Amides were the least reactive of our carboxylic acid derivatives, which meant that it was really easy to convert everything more reactive into an amide. It's harder to go backwards. So you're going to need to use heat or some other catalyst in order to accomplish that. And your yields aren't going to be great. Nonetheless, these are reactions that we want to know and more importantly, be able to draw the mechanism for. Okay, so just a reminder, right? The acyl chloride, you need to just toss in an amine. Importantly, you need two equivalents because one of them will help to mop up that HCl byproduct. So now talking about the reactions of amides, I guess real quick, also we had, similarly, just to review, we had the method of, we could have done the same thing with the acid anhydride, just tossing in the amine. If we had an ester, we can do the same thing. All right, so it was really easy to convert from one of those more reactive groups to a less reactive group. Okay. I think that the reason this brought this up, the reason that this sort of specifically brought up this reaction is because it's the most popular way to do it because your yields are really good, right? Again, this reaction was quite slow. This one's going to be somewhere in between. Okay, so now talking about amides, we can actually hydrolyze an amide back to a carboxylic acid. So going from something less reactive to something more reactive, we just need to have an acid catalyst and catalyze with heat, okay? This is going to be a reaction where the products are going to be favored. And that's because one of the things that's generated is this protonated ammonium ion, which is not a good nucleophile. So it can't go back. It is a very slow reaction, and you do have to put a lot of heat into it to get it done. Reaction mechanism. So this is going to be an acidic reaction mechanism. What do we think is going to occur first? We're going to protonate that carbonyl oxygen. Then we're going to have a nucleophilic attack because we now have this really good electrophile, which is the carbonyl carbon. That has to bump that pair of electrons up though, because you can't have more than 4 bonds for carbon. So now we get to this point here, our tetrahedral intermediate. And if we ask ourselves, do we have a good leaving group? The answer is yes, it would be this water here. But if this comes back down and kicks that off, we just take ourselves back one step, right? So the productive thing is similar to what we saw. We have to turn this into not a good leaving group, right? It's currently a good leaving group. We don't want it to leave. So the strategy is to convert it to a worse leaving group by deprotonating it. Likewise, what we want to get rid of in order to go in that forward direction is this part right here. And currently it's not a good leaving group, so we need to make it a good leaving group. Okay, so similar to what we saw before, we need to shuffle around these protons in such a way that's going to convert one to a good leaving group and leave the other one as a bad leaving group. So the book has this done in 2 steps. The first thing you're going to do is deprotonate this oxygen, right? Convert it into a bad leaving group. Next, you're going to protonate that nitrogen, converting it into a good leaving group, right? So here is our tetrahedral intermediate that has what we want. It's going to kick off that nitrogen because that's currently the best leaving group. You could do it in these 2 steps. The other thing that you can do, sort of being lazy about it, but I'm perfectly cool with that, is to say, well, this hydrogen right here is already a strong acid because of who it's bound to. So let's just go ahead and do this all in one step, right? So this will take you directly to here, and that's perfectly cool. Again, the important thing is that you've created a good leaving group on the nitrogen and a bad leaving group out of the oxygen. So then we can do what we want to do, which is to kick off that nitrogen. So this pair of electrons will come down and kick off that leaving group. Okay, and then we have to deprotonate. Finally, we're left with our protonated carbonyl oxygen. We want to deprotonate that. This is where the amine comes back into play, because remember, the amine is a moderate base. And so that'll actually snag that proton, leaving us with the following molecule. And again, the important thing about why this reaction actually favors the products, it doesn't readily go into the reverse direction, is because the ammonium ion is not a nucleophile. It doesn't have any pair of electrons that can do any nucleophilic attack. Okay, we can also have that saponification type reaction that happens, or a base catalyzed hydrolysis of the amide. Turns out to be even slower than the acid catalyzed hydrolysis, but nonetheless, important that we understand how to do a mechanism for it. You have your hydroxide. So under basic conditions, right, that first step is just nucleophilic attack, creating our tetrahedral intermediate. Now, this is definitely a worse leaving group than the hydroxide ion. Like, no matter what, it's just a stronger base. So when this pair of electrons comes down, if it kicks off this hydroxide, we're just going back in that direction, right? So that's not going to be a productive move. So instead, the productive step would be for this to come down and kick. Is first leaving group, sort of as I've been saying, if out of every tetrahedral intermediates that form, if only a few of them go in this direction, that's still progress, because anything that goes in the reverse direction just has a chance to react again. Right, so this will create our carboxylic acid and now the amide, but the amide is a really strong base, so that's going to go ahead and deprotonate that oxygen, leaving you with ammonia and a carboxylate ion. And again, you're stuck here at the products. It's not going to go in the reverse direction, because even though now we have this pair of electrons that can act as a nucleophile, the problem is that this carbon is no longer an electrophile because there's a negative charge, right? Electrophiles are electron deficient. There's a lot of extra electrons flowing around in those resonance structures. So that is no longer going to be an electrophilic carbon. We can, what does lithium aluminum hydroxide do for us? It will reduce, just like we saw before. In this case, it actually reduces not to an alcohol, but to an amine with the N, right? So it effectively sort of chops off this oxygen. Okay, the mechanism is different than what we'd expect. I bet it's actually pretty similar to what we saw in the first lecture slide for the carboxylic acids, but nonetheless, it's not one that we're going to be looking at explicitly. Important to know, though, we can reduce an amide to an amine with lithium aluminum hydroxide. Okay, now moving on to nitriles, preparation of nitriles. So the first way that we learned to prepare nitriles was using alkyl halides and an SN2 reaction, right? So remember that these cyanoions are really good nucleophiles and bad bases, so they really favor substitution reactions. So we can have a substitution reaction, and that would create our cyano group. A new way, something that we're learning about just now, is going to be to convert an amide to a nitrile, and that is using SOCl2. Okay, this is kind of weird, because the only other role we've seen for SOCl2 is when we had a carboxylic acid and we converted it to an acyl halide, right? So we were swapping a chlorine atom onto that carbonyl carbon. That is very much so not what is occurring here, right? No chlorine ion is appearing in our product. So just, although it's the same reagent, you kind of got to keep it in a different place in your brain, because it's accomplishing something completely different, okay? But this is a method of creating a nitrile from an amide, okay? And then we actually had learned before that nitriles can be converted to carboxylic acids through an acid catalyst and heat. What we didn't realize is that it actually proceeds through an amide intermediate. Okay, and then we know from last lecture that amides can be converted to carboxylic acids by the presence of acid and heat. Okay, so we already learned about the mechanism for this step here. So now we're going to focus on the mechanism for this step. How do we get from nitrile to amide? Okay, so under acidic conditions, this is going to be something a little bit different. The nitriles don't look like our other carboxylic acid derivatives. Nonetheless, we're talking about them in the same place, right? So there must be a good bit of overlap. What happens under acidic conditions is sort of similar. There's no carbonyl oxygen, obviously, but the nitrile nitrogen can be protonated. And what that does is makes the nitrile carbon an even better electrophile. So that's exactly what's going to happen. Now the nitrile carbon is going to be susceptible to nucleophilic attack. Carbon can't have more than 4 bonds. So what's going to happen? That pair of electrons is going to jump up there. Now we get to this step here. This is obviously looks a little oxygen. So in order to make that look more normal, let's do that. And that gets us to this step here. This kind of looks normal. I mean, it doesn't look like it's all that big of a, there's nothing wrong with it in the sense that everything's neutral. However, what we're going to learn is that it's not stable here. Instead, this is going to rearrange itself to an amine. Notice that these are have the same molecular formula, just a different organization of atoms. This would be considered a tautomerization. Okay, turns out that the amide is more favored than whatever this guy is. I don't know if it even has a name. Okay, but that's our goal is to just rearrange these atoms in order to get to our amide. We have these acidic conditions. So what's going to happen first is that this pair of electrons is going to come down. Hold up and grab a proton, but let me just emphasize sort of how we might be able to spot that that's the case. Okay. I need I'm trying to get to here, right? And actually I can rearrange this so that it looks more like the picture down at the bottom to sort of illustrate even more what needs to happen. Right, so I need to get rid of this double bond here and create a double bond there. That's kind of where we're going to be going. But I can't just throw that pair of electrons down there, throw that pair of electrons up there, because that would create a negative sign there and a positive sign there. And this is under acidic conditions. So this negative sign cannot be. So how do I, like, what's our strategy for making sure that there won't be that negative charge, is to protonate first. Okay, so I understand why it might not jump out to you that that needs to happen, but if you go through like, well, what are my alternatives? You should realize that the only thing that we can do here is to protonate that nitrogen in order to avoid any sort of a negative charge. And so that's exactly what we're going to see. Once we've protonated that nitrogen, that pair of electrons can come down and that pair of electrons can come up. And this is now just a protonated amide, or an amide with the carbonyl oxygen that's protonated. So the last step there would be a proton transfer, getting rid of that proton on the carbonyl carbon or carbonyl oxygen. Okay, so this is how we go from a nitrile to an amide, and then we know that also under these acidic conditions with heat, this will further get hydrolyzed to a carboxylic acid. Okay, that's a mechanism you guys should also know. That's one that we did in the last lecture. And then just like we saw with our amides, they will also react with hydroxide ions in a saponification kind of way. Right, so under basic conditions now, and again, you'll see the same sort of analogy. What's going to be my nucleophiles are obviously going to be the hydroxide ion. What's going to be my electrophile? It's going to be that nitrile carbon, right? So that goes and attacks that. Carbon can't have more than 4 bonds, so that jumps that pair up. And now look at where I'm left with. Similar to where we were before, right? So now I got to figure out how to get rid of this bond here and move it over there, because the name of the game is to get to a amide. And so what's going to happen, right? This is a strong base, that nitrogen with a negative charge. So that's going to grab a proton. Now I'm left with this kind of a situation. Well, I can deprotonate that oxygen, and this species will rearrange itself in order to get to my amide, right? So now I have the negative charge moving from being between the nitrogen and the carbon to being between the oxygen and the carbon. And then lastly will just be to protonate that nitrogen, leaving me with my amide. And again, we know that from here, if we have basic conditions, heat, etc., we're going to get to a carboxylic acid. Okay, so these mechanisms are ways of converting a nitrile to a carboxylic acid, but importantly, when you're drawing the mechanisms, the intermediate there will be an amide. Nitriles will also react with Grignards. However, interestingly, they will form ketones. So you get rid of that nitrogen altogether. Okay, this isn't going to be something that we have a reaction mechanism for, other than to say the first step is kind of what you would expect. You have your Grignard. That's going to be the nucleophile and attack that nitrile carbon. This will generate, the sort of next step would be generating this right here. It turns out that this guy will react with your acid your acid workup that you use after in order to get to your ketone. Okay, we're not a mechanism we need to know, but again, just note, nitriles will react with Grignards in order to create ketones. Okay, the reason why, ketones also react with Grignards. So why doesn't this proceed to this here? Importantly, because how you got to that ketone is through this last step here, right? So you've already added any acid that would completely kill any remaining Grignard in there. And this species right here does not further react with Grignards, right? So this is a way to generate a ketone or an aldehyde using a Grignard reagent. You don't have to worry about the multiple rounds of addition occurring, because you haven't actually gotten to your aldehyde and ketone until the second step, right? And then lastly that we're going to learn about is, last reaction we're going to learn about is very similar to amides and how they react with lithium aluminum hydride. Again, you have a reduction reaction, but interestingly, you don't get an alcohol, which is what we're used to. You get a primary amine. Okay, so this one will react. This nitrogen here will eventually become our amine nitrogen. Again, not a reaction mechanism that we have to know, although it shouldn't be too bad. So yeah, should maybe try it out.